Find the fourth degree polynomial function with real coefficients that has -2, +2, and I as zeros, such that f of 3 is equal to -150. Okay, so this problem tells me that my function has to be 0 at -2, at +2, and at I. And because complex zeros come in conjugate pairs, this function also needs to be 0 at x equal to -I. Now I have another condition, and that condition is that f of 3 is equal to -150. So when I write this function, I am going to have some leading coefficient followed by the linear factorization, which can be expressed as x plus 2, x minus 2, x plus I, and x minus I. And just to quickly refresh, I get these values by just doing the opposite. So for example here, if I add 2 to both sides, I get x plus 2. So x plus 2 is my first zero, and then x minus 2 would be my second zero, x minus I, and then x plus I wrote them backwards, but the order really doesn't matter here. So now I'm going to begin to multiply these out. And the first thing that I notice is that I have a complex conjugate. And whenever I have a complex conjugate, the multiplication is very smooth because all I have to do is get the sum of the real parts and just square them and then add them together. So for example here, I have x squared, and I'm going to add it to the real component of I, which would just be the coefficient. The coefficient here is 1. So I'm going to add 1 squared. And then 1 squared is just 1. So here this simplifies to x squared plus 1. Now here I notice that this looks a lot like a difference of squares, right? So I can rewrite this as x squared minus 4. If we were to go backwards, this would be x squared minus 2 squared, which would give me back the x plus 2x minus 2. So I get that f of x is equal to a of n multiplied with x squared minus 4, x squared plus 1. So here I'm going to use distribution to multiply these out. So I'm going to get x to the 4th with x squared. -4 times x squared is -4x squared. And -4 times positive 1 is -4. I'm going to begin by combining like terms. So I get that x squared minus 3x squared minus 4 is my polynomial, and then I have that leading coefficient in the front. To find that leading coefficient, I'm not going to make use of the fact that f of 3 is equal to -150. So here I get that f of -3 is going to equal a sub n, and everywhere I see an x, I'm going to begin to replace it by that -3. So here I'm going to begin with -3 squared minus 3, or actually this is a 4th power. This is x to the 4th, so let me go ahead and fix that. And here I'm going to put a 4. And then I get -3 times -3 squared minus 4, and recall that this should equal the -150. I'm going to begin to simplify, so I'm going to get a sub n, -3 to the 4th power. I'm going to get a positive 81. Here I'm just doing -3 times -3, so let me do that on the side so you can see. I have -3 times -3 times -3 times -3. This is going to be positive 9. That's going to be positive 9. And 9 times 9 is 81. And then this is followed by this -3, and then -3 to the 2nd power is going to be positive 9. And then I'm going to subtract 4. Here I'm trying to isolate a sub n, so I still have to simplify what's inside of this parentheses. So I have a sub n, and then parentheses 81 minus 27 minus 4. So -3 times 9, that's the -27. So if I get 81, if I subtract 27, and then if I subtract 4, I'm going to end up with 50. So a sub n times 50 equal to negative 150. And if I want to isolate a sub n, I'm going to divide both sides by 50 now. So on the left, the 50s are going to cancel out, leaving me with a sub n equal to negative 3. So I'm going to go back to my function here. And I am going to replace a sub n with negative 3. So now I get that f of x is equal to negative 3, quantity x to the 4th minus 3x squared minus 4. I'm going to distribute that negative 3 to get my final result. My function is negative 3x to the 4th positive 9x squared plus 12. Since negative times negative is positive, and then at the end, negative times negative is positive. And this is the function that satisfies all of my zeros, which are negative 2, positive 2, I, and negative I.